Hello everyone, welcome again. So today's lesson will be on the increasing levels of acidic gases in the atmosphere. So basically, as a product of our industrial revolution and the use of industry, certain gases have been accumulating in the atmosphere that have a tendency to cause acid rain, and that's what we're looking at today. Okay, so one of them is sulfur dioxide, and that comes from the burning of coal. Particularly dirty coal, like coal, brown coal, so not anthracite coal, black coal. So if we've looked at historically, sulfur levels have been monitored and are typically about 10 ppb is parts per billion. Okay, so the other usual measure is parts per million, and that's what we're measuring carbon dioxide at the moment. Parts per billion is obviously 1,000 times smaller than that, and so that's pretty good. I mean, it's well below the goal that the World Health Organization, or the WHO, established. Okay, so that's very, very good. And the reason was because we had a concerted effort to try and reduce sulfur dioxide in the atmosphere. That was a really big and one of the most successful international agreements on gaseous emissions. Okay, so that's pretty good. The other gas is nitrogen oxides. Okay, so this could be either, say, nitrogen dioxide or nitrogen trioxide. Okay, so these are quite, they're also acidic. But if you were to look at a city, any big metropolitan city like Sydney, New York, with lots of cars, what you'll see is this weird brownish haze that kind of lies over the city in the early morning. And that is caused by these nitrogen oxides. Okay, so typically when we measure them at hourly intervals, they kind of are around 150 parts per billion. So about 10-15 times higher than the sulfur dioxide. And the reason is because nitrogen oxides come out of cars. So cars are a big problem, okay, in terms of acidic oxides. And we set them at 150 parts per billion is our guideline levels. That's where we want them to be. So peak 1 hour levels in Los Angeles, for instance, so another big metropolitan city, are often 3 times this number. Okay, so in sort of the peak, when everyone's using their cars, they're all rushing to get to work, the nitrogen oxide levels could triple, to be triple this number, at hourly intervals. Okay, so cars are a big contributor to sort of nitrogen oxides. So basically, the evidence for this is quite extensive, and there's many ways to get evidence about this. So direct evidence of changes in the atmospheric concentrations of nitrogen and sulfur oxides is difficult to obtain, but possible, because basically sulfates and nitrates, which are what form when nitrogen oxides and sulfur oxides dissolve in water, are very, very soluble. Okay, so oxides of nitrogen and sulfur are very, very soluble, which means as soon as it rains in one spot, a lot of the nitrogen and sulfur come out of the atmosphere because the rain pulls them to the ground. Okay, so and the problem is also, when it rains, we could say, oh look, well, why don't we just measure the amount of sulfur and nitrogen in the rainwater, because it would have all the nitrogen and sulfur in it anyway. Now again, another problem with that is that, particularly with nitrates as opposed to sulfates, the chemicals that they form don't precipitate well, or precipitate in a form that we can study. Okay, so it's very hard for us to get direct evidence as to the increase in nitrates or nitrogen oxides and sulfur oxides, because they're soluble and they don't precipitate well. Now, also another thing is that sulfur and nitrogen oxides are much lower in concentration than other chemicals like carbon dioxide. So as I mentioned, these sulfur and nitrogen oxides are both in the parts per billion measurement scale. Okay? Carbon dioxide is 400 parts per million. So you can see that's 1,000 times more carbon dioxide than sulfur or nitrogen oxides. So the kind of dilution of carbon dioxide kind of throws our measurement ability, because it's very hard for us to detect these very low concentration sulfur and nitrogen compounds. Now, there are instruments capable of measuring this, because scientists are very clever and they have come up with them. And basically, but they've only been around for 30 years or so. Okay? So we can measure it now in this day and age. But the problem is, historically, they've been around, these sulfur and nitrogen oxides have been around for ages, since the dawn of the industrial era. Okay? So that was at least 100 years ago. So for that 70 years, we haven't measured anything. Now that's a big problem, because, well, maybe we've, gotten a bit better with this sulfur and nitrogen stuff, and so we measure lower, but there could still be some in the atmosphere from the last 70 years of industrialization. So these GCMs that they've created can measure it, no problem. But the problem with it is that the time frame is much smaller than the industrial time frame. So we are missing a lot of data, essentially, because we haven't had these very good tools for as long as we needed to. So getting direct evidence is much, much more difficult with these compounds for those reasons. However, we have collected some evidence, obviously, otherwise international agreements couldn't be formed. So there are ways to kind of infer the amount of sulfur and nitrogen in the atmosphere. And one way is to look at the ice core samples. Okay, so you go to, say, Antarctica or the Arctic Circle, and you cut basically like this, a cylinder of ice out of the Arctic. And in that ice, if you've ever watched Bill Nye talk about this, particularly for carbon, in that ice is locked gases from the atmosphere at that time. Okay, so at the bottom layer, let's say it's 1,000 years old. There's gases locked in that ice that are 1,000 years old. And then you keep going up. So the next layer might be 999 years and so on and so forth. And so you can actually, at each layer, figure out how much gas of a particular gas is present based on these ice core samples. Okay? And what we've found is that as time goes on, so as we get higher and higher and higher in the ice core to the surface, the nitrogen and oxygen, the nitrogen oxides and sulfur oxide concentrations have gone up. Okay, so that's evidence to say that we've been producing a lot of these nitrogen and sulfur oxides. So basically, like I said, they're hollow drills, collect long vertical cylinders of ice that could be many hundreds of years old, depending on the ice. And we slice them into fragments. So if we slice, it's like if you sliced a loaf of bread, for instance. Each slice is older. It could be older than another slice of it. Okay, so the deepest portion, so the portion furthest down, is obviously the oldest. Okay. So because the chemicals in the ice are dissolved in water, then they freeze. The pH of rain, so that's how we can basically analyze the situation, okay? Because they freeze together. Other evidence that we've collected could be that the pH of rain, rivers and lakes has dropped in many areas. Okay, so what does that mean? Basically, these waterways, or even the rain, the pH has gotten more acidic. Okay, so that's when pH goes down, the acidity is said to have gone up. So by monitoring the pH in these waterways, we can actually see that, well, look, the pH is going down. So that means it's getting more acidic. So that acidity had to have come from somewhere. And the evidence points towards sulfur and nitrogen oxides creating acidic rain, which then fills the waterways, which obviously means that they're more acidic than they used to be. Okay, so that's other evidence to say that the acidic oxides have actually gone up a little bit, or a lot in this case. And if you look at buildings, so we've looked at natural systems. What about our built environment? Does that reflect any change in the atmosphere? Well, yes, of course. So if you look at limestone buildings, sorry, not sandstone, limestone, any building made of limestone, you'll notice that they're pockmarked, like the rain has actually put little like dents into it. And the reason is because limestone is made of calcium carbonate. And so when it reacts with acid, the acid actually dissolves that calcium carbonate. So you can actually see the damage of acid rain on buildings, particularly old limestone buildings. So that's one piece of evidence to say that the acidic oxides are increasing. There's also other damage to forests. So if you type in acid rain into Google, usually pictures of dead forests come up. And yes, because plants are quite sensitive to pH. So if you make the soil really acidic because of the rain, they're going to suffer the consequences. And similarly, aquatic life is also very sensitive to pH. So they're not used to dealing with increasing acidity. So they again suffer the consequences of the acid rain that we've produced as industrial humans. So evidence for the increase in the concentration of CO2 includes ice core samples, study of carbon isotopes, and direct measurements of CO2 in the atmosphere. So while I've been focusing on SO2 and NO2, sulfur oxides and nitrous oxides, carbon dioxide is also an acidic oxide. However, it's not as strongly acidic as those two, sulfur and nitrogen. But we have noticed an increase in CO2 in the atmosphere, which has prompted a lot of scientists to theorize that it's contributing to the changing of our climate. Okay, so CO2 and climate change are very intimately linked. Okay, and we can get all this information from ice core samples, just like the S and N oxides. We can also study carbon isotopes. And like we said, we now have measurement devices that can just take measurements of CO2 in the atmosphere. So all these oxides are mostly man-made. So we have to, as humans, be very careful on how we utilize our industry in order to avoid adversely affecting the planet, as well as the surrounding systems, natural systems that we have available to us. Okay? So that concludes basically today's lesson on the rise in acidic oxides. So we looked at the major evidence to say that the acidic oxides have been increasing, and we've looked at how the evidence was collected. Okay, so that's today's lesson. So hopefully we can go through some questions and help you to understand how this evidence links up together. So what evidence is there that the quantities of nitrogen oxides and sulfur dioxide released into the atmosphere are increasing? So just a straightforward question from just what I've just talked about. So the increased incidence of low pH in lakes and rivers, that's the key one. That's one of the key ones. So the low pHs in the waterways tells us that rain is becoming more acidic, which has to have come from somewhere. It's very likely that it's S and N that are doing the damage. And continued damage to metal and sandstone buildings. Also limestone. So you can see that the acid actually reacts with all of these built environment features and causes damage. And the same with forests. Okay. Question 2. Atmospheric gases trapped in layers of Antarctic ice have provided us with evidence of which of the following? So, an increase in the concentration of acidic gases in the atmosphere since the Industrial Revolution, that could be it. An increase in levels of sulfuric acid in the atmosphere during the last 2 centuries, could be it, but the words are slightly different from this one, which makes me think that it's not sulfuric acid in the atmosphere, it's sulfur dioxide. So this one probably is not right based on this word. Damage to buildings, forests, and aquatic organisms over the last 50 years. Again, this is key of science, very, very key. Evidence or stuff that you measure has to give you information about your conclusion. Okay, so the conclusion here is that damage to buildings, forests, and aquatic organisms over the last 50 years, the evidence for that is Antarctic ice. No way. Okay, Antarctic ice has nothing to do with buildings, so you can't say that Antarctic ice provides evidence for damage to buildings. Okay, so that's just part of being a scientist, is being able to link the evidence to the conclusion. Okay, so C is not an answer. An increase in the rate at which glaciers are melting and the ocean level is rising. Again, this does not really tell us anything about the ocean rising. It tells us what was in the atmosphere at the time, but it doesn't tell us anything about the ocean levels. Okay, so we can't really use that evidence for that. So it's very likely A. So if we go through each of them, the evidence shows the existence of gases in the atmosphere. So that's not this one, because acid is not a gas. Sulfuric acid is not a gas. The trapped gases do not precisely provide evidence of the damages. Again, like I said, trapped gases in Antarctic ice doesn't tell us anything about the building. And so the increase in the rate at which glaciers are melting is independent of the level of acidic acids in the atmosphere. So it's probably somehow related, but in a very weak way, like really, really weakly coupled. So again, not really evidence from this that gives us this. Okay, so the answer is, it is shown how the increase in the concentration of acidic gases. Okay, so that's the answer. Okay, we went through each one and then kind of eliminated them one by one. That's how you should really approach most multiple choice questions, because some, like these two, may look the same, but they are very subtly different, and it's your ability to kind of weed them out that makes you, the difference between a really, really great student and an above average student. So outline how layers of Antarctic ice are studied. Okay, so we went through this. So you drill into the ice and then get like a cylinder of ice out. Then you slice them into layers and then analyze them. Then obviously the lowest level layer, the one that's furthest down into the ground, is the oldest, and the one closest to the surface is the youngest. And then you just figure out, you look at the gases trapped in each one, and then you make some conclusion about the temporal differences in the gas structure. You can be reasonably sure that the information about the origins of sulfur and nitrogen oxides in the atmosphere is accurate when it is obtained from which of the following? So this is a question, again, that scientists have to face all the time. How do we know that the data is correct? Okay, that's a really key point. So A, figures published by industries that produce these oxides, as industries have the true figures. That could be true, in the sense that industries do have the figures. The problem is, do you trust the figures if it may harm their business? Probably not. So I wouldn't say that this would be the best way to study a particular phenomenon, because I've heard many petrol companies talk about the fact that there's no global warming. Every scientist in the world basically says that there's global warming. So who am I going to believe? So that's one typical example of that. So probably this is not a good way to approach studying something. So B, similar information obtained from reputable sources. Okay, that's very likely. So scientific journals are peer reviewed. So what that means is scientists try to publish a paper, publish some results. Those results are scrutinized by other scientists. And then if they pass the scrutinization stage, then it's useful, it's knowledgeable. So you can trust that it's passed a certain level of scientific validity. So this is probably a good way to look at it, but we'll go through the other ones just in case there's a better one. So newspaper articles, as journalists know how to obtain up-to-date information. Again, they do know how to get information, but again, as I've read many newspapers in my life, a lot of them are not very accurate. So I wouldn't trust them as a scientific knowledge base. So again, that's probably not a good site of information. And any internet site, as these often contain the latest correct information. Again, the internet is a great place to get up-to-date information because it's how we connect with everything now. But because anyone can change a site, anyone can create a site, possibly with no scientific background, I wouldn't trust them as a way to study a particular phenomenon. So I would go with B. Scientific journals are key. They're the best way to understand, to be reasonably sure that the information is right. Okay. So again, as I mentioned, industry has biased results because they don't want to hurt their business. Newspapers, not accurate because they're written to sell a story. So you can see here in both cases, the motivation is getting money. So neither of those two. And most internet sites are updated by the public, which make them inaccurate. So again, people with no scientific background can say that they know a lot, and that's wrong. So reputable sources are accurate. So scientific journals are great. The UN scientists are working really hard to produce these things, so that's probably a good way to ensure that your results are right. Okay. Why are scientists concerned about the increasing volumes of nitrogen dioxide and sulfur dioxide being released into the atmosphere? Okay, so again, we'll go through each one. So they are insoluble and not washed out of the atmosphere. That's not really a concern because they are soluble. We went through this. B, they are soluble and lower the pH of rain. That could be a concern because pH of rain is important for other systems. So we'll hold on to B unless something better comes along. Sulfur and nitrogen are important components of living tissues, so are required for growth of living things. Again, that's possible. Nitrogen is very important for our DNA. It's also very important for plant growth. But sulfur, not so much. And I don't know if this could be considered the best answer. D, they contribute to the depletion of ozone and to the greenhouse effect. A lot of people say a lot of things contribute to the ozone hole or greenhouse effect. This definitely doesn't apply to the greenhouse effect. So, or the depletion of ozone. So, definitely not D. Okay. They are usually soluble producing acids. Okay. So, definitely not this one because this says they're insoluble. Yep, again, this doesn't really concern the scientists because living tissues are the effect of them is different. And the depletion of ozone is from CFCs and halons, and the greenhouse effect is CO2. So it's not this one. So it must be B, because they're soluble and lower the pH. So that's damaging to the environment. Okay, so that's the answer. So hopefully you've learned something about the increase in acidic oxides in the atmosphere. We've looked at how we can gather evidence and how we can sort of validate that evidence. So hopefully you'll think about maybe what the consequences of these oxides are, and how to assess scientific methods. So thank you for listening, and I look forward to seeing you at our next lesson.